Okie doke. Let's go first.
I have a question on the lab assignment for
Yes.
question 2 and maybe 4. I'm kind of confused. Like, what kind of we drawing on the problem 4?
Well, let me take a look at the lab assignment.
Yeah, 2.
I have to open it up. And then I'm going to change my share screen with you so you can see what I'm writing.
Mm-hmm.
Okay, module 10, right?
Yeah, the valence bond theory.
Lab assignment. Okay, what number first?
2 and 4.
Number 2, make a table
Yeah.
of the types of hybridization. So let me change my share. Okay, types of hybridization. There's SP,
Yeah.
SP2,
Mm-hmm.
SP3, SP3D, and SP3D2. Okay, so those are the types. I just hit the autofocus, so if things looked a little weird for a second, it's because of that. Okay, let me go back to the questions. Okay, the number of hybrid orbitals. Two, three, four, five, six.
Mm-hmm.
The number of unhybridized P's. 2, 1, 0, 0, 0. The molecular geometry for each. No, I'm sorry, that's the next problem. Drawings of the hybrid and hybridized p orbitals for each. Well, this one, there's no unhybridized p's, so I'm going to do this like this because the drawings end up being kind of big.
Yeah.
So I'm going to start with this one. Each one of them is sp3d2. So
Okay,
there's
yeah.
6 of them. Now sp3d5 is going to look like this. So there's 5 of them. For the 4, it's going to look like this. Are you with me?
Yeah. I just want to check it. I do it right now.
For this one, the best way to draw is like this. Those are the sp2s, and here's the p.
Mm-hmm.
And this last one, it's going to look like this. This is sp, this is sp, this is p, and this is p, where it's supposed to look kind of like this. The sps are on the x-axis. One of the p's is on the y-axis, and the other p is on the z-axis. And that's it.
Yep. So I have a quick question about that. Like, so the unhybridized, is that like the one that P doesn't have the electron, right?
No, it doesn't mean it doesn't have electrons. It means that it's not hybridized. So here, when you have this is a 2s and this is a 2p, and these are not hybridized. Okay, so unhybridized, right?
Yeah, so it doesn't have it.
You can take 2 of them and hybridize them.
Mm-hmm.
And the other 2, here I'm going to put P here and S here. So these two P's aren't hybridized. These are hybridized, and this is an SP and this is an SP. These hybrids are less stable than an S, and they're more stable than a P. But notice we have 4 orbitals here. And when we hybridize them, we still have 4 orbitals. So the P's don't mean anything. Let's say that you have an atom that has 4 electrons in it. So it looks like this, right? Are you with me there?
Yep.
So if you put these 4 electrons over here, they're going to look like this. 1, 2, 3, 4. And there's nothing in the P's now. But technically, what usually happens here is we do this. And then we bond.
Actually, the screen is kind of, they have like the white spots. Yeah, that's good.
Can you see this now?
Yeah, yeah.
Okay.
Okay.
So this is not hybrid and this is hybrid.
Yeah.
So the idea here is that the P's are still there. And they may or may not have electrons. It depends on how the valence bonding goes.
Yeah.
All right.
No. And therefore, I just want to lay a quick question. So I draw the valence bond is like a molecular geometry or kind of.
Are we still on number 2?
Oh no, problem 4.
Problem 4.
Yeah.
Draw a figure that shows valence bonding in allene. So first of all, to do this, you need the Lewis structure.
Yeah.
And the Lewis structure is going to look like this. Okay, can you see that?
Yeah, yeah.
Okay, this is sp2, this is sp, and this is sp2. Now I'm going to draw this guy first. Okay, those are the 2 sp hybrid orbitals, okay?
Yep.
And then there's this. This is an unhybridized P. And this is an unhybridized P. So do you remember that drawing over here?
Yeah.
So I've drawn this right here. And in the middle of this is a carbon.
Okay.
Now this guy's sp2, correct?
Yeah.
So I'm going to draw this. And here, the P is going to be here like this.
Okay.
There's the P, and here's the other sp2. So this is supposed to be a flat triangle, kind of like this. Are you with me here or not? And the P is going in and out of that triangle. So the P is really like this, my pen sticking straight up. But we draw it so it looks like the z-axis coming out. Are you with me there?
Yeah, got it.
Okay, so this is a carbon. This is a sigma bond right here. The sp and the sp2 overlapping. Now here, this P and this P, they overlap. This P right here and this P right here overlap, and that's a pi bond.
Okay.
Now the other one I'm going to draw is going to look like this, sp2. And instead of drawing it like this, I'm going to draw it like this. So here the triangle is not like this. The triangle is more like this. Do you understand the drawing?
Yeah.
Okay. So the P is like this. This P overlaps with this P. And the reason they can do that is because they're parallel to one another. So do you see these 2 P orbitals right here that I'm pointing at?
Yeah.
Now, look at my picture here, my image. Those two p orbitals are parallel, going straight up and down, and they overlap. Okay.
Okay. Yeah.
So that's what these lines are. They show the overlap. Now it looks like that's a bond and that's a bond, but it's not. This is half of a pi bond, and this is the other half of the pi bond. So together, what does this make if that's half of a pi and that's half of a pi?
Pi bond.
One pi bond.
Yeah.
Now over here, do you see these two p orbitals?
Yeah.
Now look at my photo or my image. Now, do you see my arms are straight out?
Yeah.
Those are the two p orbitals, and I'm gonna talk so that you can see my image. And when they are side by side, they also overlap. And this is that drawing there. So this is half of a pi bond. This is half of a pi bond. And altogether, what do you have there?
Pi.
A pi bond. Now, to finish it off, I'm going to put this here. This is hydrogen. I'm going to put a hydrogen here, a hydrogen here, and a hydrogen here. And this is what the bonding looks like. Now let me draw it so that you can see what this is representing. So this is the representation of this. This shows all the bonding. This shows the geometry. Do you see that this is sp2 and trigonal planar?
Uh-huh.
Can you see that this is sp2 and trigonal planar?
Yeah.
And can you see that this is sp and it's linear?
Yeah.
And of course, the bond angles here are 180, 120, 120.
20.
So this doesn't really show you what's going on here, but this is how we understand what is happening here. Now, some interesting things here. We can look at this molecule and see how many sigma bonds there are. So this is a sigma, 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 this is a sigma. So side to side overlaps are pi bonds. When they're head to head, they're called sigma bonds. So if we take a look at these sigma bonds, you can see that this is a sigma, this is a sigma, this is a sigma, this is a sigma. And right here, one of these is a sigma, the other's a pi. One's a sigma, the other's a pi. The lesson you're supposed to learn there is that when you look at a molecule like this, if there is a single bond, it's a sigma. If there's a double bond, one is sigma, one is pi. If there's a triple bond, one is sigma and two are pi. Okay?
Yeah.
Does that help you out?
Yeah, yeah.
Okay, excellent.
Thank
I really
you.
should have made that little two a subscript, shouldn't I? All right. Who's next? No one, huh? Okay. Well, then let's go back to the gases. Gases and their properties. Last thing I think I talked about was STP. And we also talked about the kinetic molecular theory of gases. So the next thing I want to talk about for gases and their properties are, let's see, what do I want to do? I want to do Dalton's law. Dalton's law of partial pressures. Okay, so that's where we're going now. Okay, so when we talk about Dalton's law of partial pressures, this is specifically for a mixture of gases. Up until now, we haven't really considered pure gases versus mixtures of gases. Dalton's law is really specific for mixtures of gases. And Dalton's law says that the pressure, well, actually, I want to point out this for the mixture of gases, the temp is the same for each gas. So if I have a container here and we've got gas molecules in here, and what I'm doing here is I'm representing the different gas molecules as either X's or O's. So how many gases do we have in here? 2 gases. And here, let's just add another couple of O's so that we see that we don't have to have the same number of molecules of each. So we've got 6 of the spheres and 4 of the X's. Okay, the temperature is the same for each gas because of thermal equilibrium. It's hard for one of these gases to be hotter than the other. The volume is the same for each gas. So if we were to use an ideal gas law just for the round ones, we would use the volume of this container, whatever that is. If we were to use the ideal gas law for these X's, we would use the volume of this container. So the temperature is the same for each gas, the volume is the same for each gas, and does not have to be the same. And usually it is not. And the pressure of each does not have to be the same. Okay, so if this is the case, this means that the moles total is going to be the moles of gas 1 plus the moles of gas 2, and so forth and so on, for as many different gases are in there. And this is actually Dalton's law of partial pressure right here, that the pressure total is going to be the pressure of the first gas plus the pressure of the second gas plus the pressure of each gas that's in there. And this is where N1 is equal to the moles of gas 1, N2 is equal to the moles of gas 2, P1 is equal to the pressure of gas 1, and we call this the partial pressure of gas 1. Now, this pressure of gas 1, when we call it the partial pressure of gas 1, to me, that was always confusing when I learned this. When we say partial pressure of gas 1, to me, it means what is not the full pressure of gas 1, but part of the pressure of gas 1. And that's not what this means. When we say partial pressure of gas 1, that means the full pressure of gas 1. So if we're looking at the full pressure of gas 1, why do we call it a partial? And it's because here it's a partial of the total. So a better phrase for this, rather than calling it the partial pressure of gas 1, we would call it the pressure of gas 1 that is part of the total. The pressure of gas 1 that is part of the total. So if you understand what I've written here, that the partial pressure of gas 1 really means the pressure of gas 1 that is part of the total, give me a thumbs up. Okay, great. Now, what I want you to do, if this is the partial pressure of gas 1, I want you to think about this in your head, what this would be called. And when you're ready for me to tell you, give me a thumbs up. Just think about it. Maybe even write it down. What do you call that? Okay, great. This should be called the partial pressure of gas 2. Now, why is it called the partial pressure? Because it's a part of the total. Are we good on that? If we're good on that, give me a thumbs up. Great. Okay. Now, there's something else they talk about in the book. It's called the mole fraction of gas. We'll say gas 1, but this could be any gas. It could be gas 2, gas 3, gas 4. So the mole fraction of gas 1, and actually in the book they use the letter A. The mole fraction of gas A is the moles of gas A over the total moles of gas. Now that's a lot to write. So here's the way it's written in the book. N sub A is the moles of gas A, and N's, usually they write TOT for total rather than just T. And this is the way to calculate the mole fraction of gas A. Okay? Now, I want to point out something to you here. If we have PV equals nRT, and if we have P sub A, V is equal to N sub A, RT, you'll notice I did not put T sub A and V sub A. And the reason I didn't do that is because when we look at this equation for B, the V's are the same and the T's are the same. Remember back here where I say T is the same for each gas and V is the same for each gas? So in this case, I don't want to say V sub A because that makes me think that the volume is different than for B. They are the same volume. Okay, so what this means is that P sub A is equal to N sub A VRT. Oh, my bad, over V. The reason I want you to see this is that you should see that P sub A is proportional to N sub A, because the temperature is a constant for the mixture, because the volume is a constant for the mixture, because R is a constant for the mixture, the pressure is proportional to the moles. So that means we can actually calculate the mole fraction of A by taking the partial pressure of A and dividing it by the total pressure. These, in fact, are the same, will give you the same result. So you should probably know both of these. This is the real definition for what's called the mole fraction, but this is another way to calculate it. You can calculate the mole fraction without actually knowing the moles. If you have the partial pressures and the total pressure, you can still calculate the mole fraction. Okay, are you guys okay with that? Okay, let's take a look at a problem based on mole fraction of gas A. So I'm going to take one out of the book, and I'm going to pick one at random. Let's see, this is chapter 9, I think. And no, apparently it's chapter 10. Okay, so here you can see we've got gas mixtures and Dalton's law. Let's take a look at this problem right here. And I'm going to zoom in on this a little bit so that you can read it. And if you go back and watch this video, what you may want to do with this is play this, freeze the video, and write down the question. So I'm going to go ahead and read the question to you here. It should come into focus in just a moment. So for those of you who go to the eye doctor regularly, you're used to seeing that go in and out of focus. A cylinder of compressed gas is labeled composition mole percent 4.5% H2S, 3.0% CO2. The balance is N2. The pressure gauge attached to the cylinder reads 46 atmospheres. Calculate the partial pressure of each gas in atmospheres in the cylinder. So I'm going to write that information down now. We've got that the partial pressure of H2S, actually, I'm sorry, we don't have that. CO2 and the partial pressure, whoops, of N2, these are what we want. Now, the mole percentage of H2S is 4.5%. The mole percentage of CO2 is 3.0%, and the mole percentage of N2 is going to be 100 minus 4.5 minus 3.0%, which is going to be 92.5%. So does everyone understand? Whoop. Let me zoom out so you can see what I've written. Sorry about that. Once I start solving it, I get carried away. Okay, so this is what we want. We want the partial pressure of each gas. And we're given that the mole percent of H2S is 4.5%. The mole percent of CO2 is 3.0%. And the balance is the mole percent of nitrogen. And here, all of these should add up to 100%. So that's how I get this 92.5. I subtract 4.5 and 3.0 from 100. Now, to get the mole fraction from a percentage, you take the mole percent and divide by 100. So if we want the mole fraction of H2S, that's going to be 4.5% divided by 100%, which is 0.045. So that's the mole fraction of H2S. Any questions there? And this is how you show the work. So you know how in math class they say, well, whenever you have a percentage, just move the decimal over 2 places. And they tell you, but the caveat is when you move the decimal over, you have to memorize that you move it to the left. And to me, that is the stupidest thing in the world to tell people, because there's no understanding in why you move it to the left. The best way to remember how to change a percentage into a fraction is to divide by 100. Okay? Divide by 100. So what is the mole fraction of CO2 equal to? What would the work look like? Go ahead and do the work. Give me a thumbs up when you're done. And do the same for N2. Calculate the mole fraction of each. Excellent. Hey, Harry, I got a question for you.
All right.
Were you out for a walk or a run this morning about 8:30?
Yeah.
Ah, okay.
Wow.
'Cause
Yeah.
I saw you. It was like
Oh.
on the corner of Henderson and something else.
Yeah. I was out with my mom. She saw me with
Yeah.
someone else.
I thought I recognized you. You're a rather tall bloke.
Yeah. Oh.
Compared to me, I'm 5'6", Harry.
Yeah. I'm like 5'10" or something.
Well, to me, that's a tall bloke. I'm short.
Yeah. Look
Okay.
at that.
At any rate, let's take a look at this. You should have gotten 3.0% divided by 100% and 0.030. If you don't have the 0 on the end of this, you did it wrong. 2 zig figs, 2 zig figs. Okay? And here we have 92.5 over 100. So you get 0.925, 3 zig figs and 3 zig figs. Okay, now do you remember how I told you that the mole fraction of A is equal to the moles of A over the moles total? What else did I tell you? The mole fraction of A is equal to the partial pressure of A over the pressure total. The other thing we're given here is that the pressure total is 46 atmospheres. So if I want the partial pressure of H2S, I could do this. The mole fraction of H2S is equal to the partial pressure of H2S over the pressure total. Now, do we have the mole fraction of H2S? You bet your bippy. Do we have the pressure total? You bet your bippy. Do we want the partial pressure of H2S? You bet your bippy. So this comes out to the partial pressure of H2S is equal to the mole fraction of H2S times the pressure total. And mole fraction has no units because you're taking the moles of one thing, dividing it by the moles of the other. So there are no units. The same with the you calculating it using pressures. If you have atmospheres here and atmospheres here, you get no units. So this has no units. This does have units. All right. So you put these two together, and can you see how 0.04 is almost 0.05? Now, 0.05 is not half, but I like to think of it as half. This is actually a tenth of a half, right? So here's what I'm going to do. Half of 46 is 23. And then a tenth of 23 is 2.3. And since this is not really 0.05, but a little less, I'm going to say the answer is 2.2. That's my ish. So let's see what we get. And we don't get 2.2, we get 2.1 ATM. And that is the partial pressure of H2S. If you're okay with that, give me a thumbs up. Now, do you see just how useful this is to us? Not only knowing this, but knowing this. It's really convenient when you're doing problems. Otherwise, we'd have to do a whole lot of work calculating the moles of this and the moles. It would just be a pain in the rear. So what I'd like you to do now is I'd like you to calculate the partial pressure of CO2 and calculate the partial pressure of N2, just like I've done here. And when you get those answers, give me a thumbs up. And take the time to write it out on your piece of paper as if you were taking an exam. Okay, so when you get your answers, give me a thumb up. Okay. So I'm going to do the work down here in this little space. The partial pressure of CO2 is going to be 0.030 times 46 ATM, and I get 1.4 ATM. The partial pressure of N2 is going to be 0.925 times 46 ATM. And here I'm going to get 44 ATM. Now, you'll notice I have 43.7 up here, and that's to help me know where I need to round this. Because of the 46, we only get two significant figures. Any questions about that? So the answers are 2.1 ATM, 1.4 ATM, and 44 ATM. And when we add these all up together, they should be 46. Now, they don't add up to 46. In fact, they add up to, what do they add up to? 5, 6. They add up to 47.5. Now, where's the error? The error comes here with this guy because we have to round to the ones. And this actually adds up to 48, I should say, because when we add these up, we can only report a number to the ones. Okay, so that's a partial pressure problem. Let's take a look and see if there's another interesting one here. I don't like any of the other ones. There's another one that is part of your homework, and it's this one. I'm not going to show you how to do this problem. I'm going to explain it to you. And so hopefully the words will help you to understand it. Okay, let me zoom in on it. And let me describe the problem to you. And this is all we really need. We don't need the rest of this garbage up above. This tells us everything. It also tells us that the people who make the drawings in this book are a little weird. Okay, so this drawing up here shows two containers separated by what's called a stopcock. And you see that little hole in the middle of the stopcock? That allows the gases to go through. But when the hole is perpendicular to the containers, no gas can go through. So when you turn this stopcock 90 degrees so that the hole is parallel to the containers, gas can go through, as you can see in this drawing. Now, in this container to the left, we have 3.0 liters of helium at 145 millimeters of mercury. In the container to the right, we have 2.0 liters of argon at 355 millimeters of mercury. So the pressures are different and the volumes are different. Now, I can understand that it's hard to show the pressures being different when they're different gases. I mean, how do you show that one has a greater pressure? It's tough to do, especially when these containers are rigid. But come on, the left one's a 3-liter container and the right one's a 2-liter container. They look like they're the same size to me, don't they? I mean, how much effort would it take to make this sphere a little smaller? This is one of the problems I have with this little drawing, is just a little more effort and it would look so much better. Nonetheless, when you open the stopcock, the gases mix. And the question is what is the pressure of the argon gas after they mix? And what is the pressure of the helium gas after they mix? And then what is the total pressure? Because this is a Dalton's law thing where the total pressure is equal to the pressure of helium plus the pressure of argon. So does anyone have any ideas on how to solve a problem like this? If you do, just throw it out there and tell us what you think. Because it's a tough one, and I'd like to hear, what you're thinking. It's okay to not really know. No one, huh? Okay, here's a hint. I want you to imagine that this container here, the blue one, had no gas in it. It was 2 liters and no gas in it. And because there's no gas in it, there's no pressure in it. Is everyone okay with that idea? Give me a thumbs up if you're okay with that idea. Okay, so imagine we turn this stopcock. What's going to happen to the helium gas when we turn the stopcock? The helium gas will flow through here, go into this container, but some of it will be in this container. And roughly 3/5 will be in this container and 2/5 will be in this container of our helium gas. And the reason I say 3/5 and 2/5 is because this is 3 liters and this is 2 liters. So naturally, they will partition based on the volume. Okay, so could you calculate the pressure of the helium gas after you open the stopcock if there was no argon in this container? If you think you could do that, give me a thumbs up. Does it sound like a P1V1 over N1T1 is equal to P2V2 over N2T2 type of problem? And does it seem like the temperature is not going to change, so that falls out of the equation? The moles of helium gas do not change, so that falls out of the equation. So we end up with P1V1 is equal to P2V2. Does that seem reasonable? I'm going to get rid of your thumbs because I don't know if you think it's reasonable. Okay, solve the equation. Find out P2 for the helium gas if there's no argon in the right-handed bulb. Give me a thumbs up when you're done. So this is one of the parts where you may make a mistake. Let me show you what I've written here for part of my solution here. So I've done this P1V1 is equal to P2V2. P2 is P1V1 over V2, 144 millimeters of mercury times 3.0 liters. Here, V2 is the final volume, which is the sum of both spheres. So if we do this, we can see that the answer is going to be a little bit more than half of 144. Half of 144 is 72, so the answer is going to be like 90-ish, right?
Isn't it 145?
Oh, thank you. So we get here 87 millimeters of mercury, and we only get 2 significant figures because of the 3.0 and the 5.0. So that's the pressure of helium after it's allowed to go into the other bulb, right? Now, turns out this is the partial pressure of helium when they mix. You get to treat each gas as if it's the only gas in the container. And then you say, okay, so if I put them both in the containers, this will be its partial pressure. Pretty tricky, isn't it? Okay, now calculate the partial pressure of argon based on the same principle. When you're done, give me a thumbs up. If you can't see the pressure on the argon, it's 355 millimeters of mercury. Sorry, I didn't see the thumbs up. I was distracted. I get 140 millimeters of mercury. If you wrote 142, that's got too many significant figures because you have 20 divided by 50. So if you wanted to show the work here, it would look like this. And this has 2 zig figs. This has 2 zig figs. So this only gets 2 zig figs. Any questions here about this problem? This happens to be one of your assignment problems for partial pressures. Okay, let's move along. So when they talk about the kinetic molecular theory of gases, one of the things they tell you is that the kinetic energy is proportional to the temp in Kelvin. And this is really the average kinetic energy. Now, kinetic energy of a particle is equal to mv squared over 2, where m is the mass of the particle and v is the velocity of the particle. Now here, this is regardless of the identity of the gas. The kinetic energy is proportional to the temp Kelvin. So for 1 mole of H2 at STP, it's got the same kinetic energy as 1 mole of xenon at STP. Now, why is this remarkable? Why is it the same kinetic energy for both of these? What's remarkable is that the mass of H2 is 2.02 AMUs, and the mass of xenon is 131.3 AMUs. So if we were to draw these, this would be a H2 and this would be a xenon. How can these tiny little particles have the same kinetic energy as these huge particles? And the answer is here in this equation. If the kinetic energy of H2 is equal to the kinetic energy of xenon, that means that mv squared over 2 is equal to mv squared over 2, but this is the mass of H2 and the velocity of H2, and this is the mass of xenon and the velocity of xenon. So we can change this into something that looks like the following. We can say that the velocity of H2 squared over the velocity of xenon squared is equal to the mass of xenon over the mass of H2, and the 2's fall out. So what is this telling us here? Well, look at this guy here. This says that the mass of the xenon is well, we know that the mass of the xenon is far bigger than H2. So here, this is going to be greater than 1. What does it tell us about this? This is also greater than 1. So that means that the velocity of H2 has to be greater than the velocity of xenon. That's how they have the same kinetic energy, is that smaller molecules are moving faster and bigger ones are moving more slowly. So how am I going to show that up here? Fast, slow. Okay, so here's one of the ideas that you have to understand is that the kinetic energy is the same regardless of the gas, but the way that works is that large molecules are moving more slowly and small ones are moving faster. The other thing you have to understand is that there is a distribution of velocities. So if we do something like this, number of molecules, and we do the speed, this might be xenon. And this would be H2. What I'm trying to point out to you here is that the molecules themselves are not always traveling at the same speed. There's a distribution of velocities, a distribution of speeds. I use speed and velocity interchangeably, which is a big no-no in physics. But you know what? I'm not a physicist. The difference between speed and velocity is simple. Speed is just how fast you're going. Velocity is how fast you're going and the direction you're going. So if I were driving to Arcata and my velocity were 50 miles per hour, if I were driving from Arcata back to Eureka, my velocity would be negative 50 miles per hour because you associate direction with the velocity. Speed, no direction needed. So if I drive from here to Arcata and my speed is 50 miles an hour, naturally when I drive back, my speed will probably be 50 miles an hour because I'm an old fart and I watch the speed limit. Okay, does everyone understand that there's a distribution of velocities, but that the mean distribution, the mean velocity will be rather different depending on the size of the molecule? If you're okay with that, give me a thumbs up. So let's actually write that down. There's a distribution of speed. Smaller molecules skew to the right, higher speed. So do you understand what I mean when I say skew? The top of the mountain moves to the right. And naturally, if the smaller molecules skew to the right, what do the larger molecules do? They skew to the left. Okay, now here, it's more useful to talk about RMS speed, because you don't want to look at each individual molecule, you want to use the average. So for the average, we have what's called the RMS speed. That stands for root, mean, square, speed. RMS speed. So let's look at RMS speed. So RMS speed starts with this idea here that we're going to use U is the speed of a molecule. U squared is the speed of a molecule squared. And U squared with a line over it is the average of the speeds squared. So you take each velocity or speed, you square it, and then you get the average of those. Now, it turns out that the U squared, so this is called the mean square velocity or speed. That's what this is. So this bar here means the mean. The mean is different than the median. The median means the middle value. The mean means the average. Okay, now it turns out that this is equal to RT over the molar mass of the molecule. And actually there's a 3 in there. And this R is actually like 8.31 joules. I can't remember now, joule seconds or something like that. I have to look it up. You don't ever, I don't know what this is. I'm going to put a question mark there, and you don't need to know what it is. Okay. So this is a very useful equation, and this is the molar mass. So we could do this for gas A. We could do this for gas B. So here, we're talking about two different gases, like maybe xenon and hydrogen. Are you okay with these two equations here coming out of this? Okay, now let me show you how we use these two equations. So here are the two equations again. Same two equations I had written before, but now I'm going to do something tricky with this. Now here, remember, this is called the mean square velocity. Well, when we talk about the kinetic molecular theory of gases and that the kinetic energy is proportional to the mass times the volume squared, or excuse me, the mass times the velocity squared, we don't really want the velocity squared. We want to know the velocity. So we want to be thinking about what is the velocity of these particles, not the square of it. So we're going to do two things. One of the things is we're going to divide this guy by that, and therefore divide this guy by that. And we're going to take the square root of everything. So when we clean this up, we get now you'll notice I put everything underneath the square root over here and and I did not do that over here. So the way to think about this is the average velocity or speed. And it's actually the RMS speed. So why do we want the RMS speed? The reason we want this is because this speed tells you how fast that gas will mix with other gases or how fast that gas will fill a room. Naturally, the larger the RMS speed, the faster the molecules, the faster they will fill a room. So does everyone understand that connection between RMS speed? Has to do with how fast the gas will spread. Is that clear? Okay, the other thing to notice about this equation is that over here, you'll notice that m sub b ends up in the numerator and m sub a ends up in the denominator because of the nature of the equation. So that's a little thing for you to do algebraically to prove to yourself that m sub b ends up in the top and m sub a ends up in the bottom. Okay, so here, when I talk about how fast something can mix or how fast something can spread, we have two things called diffusion and effusion. Diffusion is how fast or a gas spreading. And effusion is a gas moving through a small opening. If you've watched my lectures, you have seen that for this, I basically drew something like this. Here's a gas. You open the lid, and what we're talking about is how fast these particles get out into the room. This is diffusion. Effusion would be when you have small little holes here, and it's how fast the gas gets through that tiny little opening and gets into the room. That's the big difference. Okay, so effusion is a gas moving through a small opening. And here, if you have a faster speed, you're going to have faster effusion and diffusion. Does that make sense that the faster your speed, the faster you're going to mix, or the faster you're going to get through small openings? Does that make sense? So when we talk about speed, speed is like is proportional to rate. So this equation, since the speed is proportional to the rate, we say the rate of gas A over the rate of gas B is equal to the square root of the molar mass of B over the molar mass of A. Now, for the rate, it must be moles or molecules per time, or it must be liters or volume per time, but not mass per time. Okay, so when you do problems like this, it's got to be moles per time or liters per time, but not mass per time. And it's important to remember that. So let's take a look at this law. This, by the way, is called Graham's law. And this is one of those gas laws where you can't really get this law from P1 V1 equals P2 V2 or PV equals nRT. You can't get it from there. So this is one of those laws that, you know, on the exam, you probably want to write it down somewhere on your note card. Is that clear? And when you write it down, if you wanted to, and you want to be real tough, you could remember how to derive it, but why bother? All right, let's take a look at a problem that deals with Graham's law. So let's start off with 47 because we don't need to do any work for it except for in our heads. In each pair of gases below, tell which will effuse faster. Now, remember for the rate of A over the rate of B is equal to the molar mass of B over the molar mass of A, right? Whoops. This thing zooms so incrementally, it's a pain. Okay, so the rate of A over the rate of B is the molar mass of B over the molar mass of A. So when we talk about which will effuse faster, so rate A, let's say rate A is 10 and rate B is 1. This tells us that we want the molar mass of B to be larger than the molar mass of A, right? Oh, you can't even see that. I'm just going to leave that off there. So the idea here is that smaller molecules diffuse faster. So what's going to diffuse faster, CO2 or F2? Well, CO2 is 44, F2 is 38. So who's going to fuse faster? F2, because it's smaller. So who's going to fuse faster, O2 or N2? If you think it's O2, pick go slower. If you think it's N2, pick go faster. Correct, N2 because it's smaller. Now, is it going to effuse a whole lot faster? No, not much at all. How about here, C2H4 or C2H6? Which will effuse faster, left or right? Left is go slower, right is go faster. Oh, vote again. Correct. We don't even need to add the numbers up. We can see that in this one, there's 2 fewer hydrogens on the left, but the same number of carbons in each. So the left is smaller, it will effuse faster. How about these two guys? Which is going to effuse faster? Now this one's a little tougher because you've got a mixture of things. Okay, so what is the total of this? Well, each chlorine is about 35. 35 times 3 is 105. Fluorine is around 20, so that's 125. Plus carbon gives us 137. Over here, we have 4 fluorines, which is really close to 80, plus 2 carbons, which is going to put us close to 100, plus 2 chlorines, which is going to put us up to 170. So this is 170 and this is 130-ish, which is going to fuse faster, the one to the left, because it does weigh a lot less. Okay, any questions about that? '48 looks like an interesting one. Argon gas is 10 times denser than helium gas at the same temp and pressure. Which gas is predicted to effuse faster and how much faster? So try to muddle your way through this one and see what you can figure out. And when you think you have an answer, give me a thumbs up. I'm going to put a pause on this because this is a tough one. Okay, so this figure here is to show you what they mean by argon is 10 times more dense than helium. If you have 4 argon particles compared to 4 helium particles, each argon weighs 40, each helium weighs 4. So this would be 160 AMU per whatever volume, and this would be 16 AMU per whatever volume. And you can see that this density is 10 times less than that, or this density is 10 times greater than that. So that's what they mean by density. Okay, which gas is predicted to effuse faster? And the first question and answer is helium. Why? Because it's smaller. And therefore, RMS speed is greater. Okay, what is the, how much faster? Okay, now this is a tough one. So we know that the rate of 1 over the rate of 2 is equal to the molar mass of 2 over the molar mass of 1. I've switched my labels here. Instead of using A and B, I'm now using 1 and 2. But I'm going to now cross that off, and I'm going to put the rate of helium over the rate of argon is the molar mass of argon over the molar mass of helium. Okay, so here, when I get the rate of effusion here versus the rate of effusion to argon, I'm going to get how much faster. So here, the molar mass of argon is 40 grams per mole and 4 grams per mole, which is the square root of 10. And the square root of 10 is like 3-ish. So the helium will fuse about 3 times faster than the argon. Any questions about that? Are you guys okay with that? Okay, there's two more things I want to cover, and they won't take long. One is density of gases. To calculate the density of a gas, the density of the gas is equal to the mass divided by the volume. And so we can write M over V. Now remember, we have PV equals nRT. And let's see if I can remember how to do this. We can also say that the moles of gas is going to be, let's see. Trying to think about how to derive this equation. If you take the molar mass of a gas, which is going to be grams per mole, and you multiply it times N, you're going to get the mass of the gas. So here we can say that the molar mass times N is equal to the mass of the gas. That comes from here. The molar mass of a gas times the moles of the gas is equal to the mass of the gas. And the way I know this is because this is grams per mole, this is moles, and so we get grams. All right. So that means that N is equal to the mass of the gas divided by the molar mass of the gas. So we can take that and substitute that in here and get PV is equal to M over M RT. Now I can rearrange this and get P M, actually I'm going to leave the M there. P is equal to M over V M RT. So what I did is I took the V and put it on the other side. Now what is that? That's density. So this is an interesting equation here. P is equal to DRT over M. And you can write this really two ways, that the density is equal to PM over RT, or you could write that the molar mass is equal to DRT over P. So what I'm trying to tell you is that you can calculate the density of a gas simply from knowing its pressure, its molar mass, the gas constant, and the temperature. Likewise, you can calculate the molar mass of the gas by knowing its density, the gas constant, the temperature, and pressure. Okay. And the last thing that I want to talk about was actually when an ideal gas is not an ideal gas. Okay, and the answer is there's only one answer. It's not an ideal gas when it's a liquid. So this should make you scratch your head. What the heck is he talking about? What do you mean when a gas is a liquid? That's silly. Well, here's what I want you to think about. Has anyone ever seen a butane lighter? When you have a butane lighter and you shake it, and in fact, I think I have one right here. I have a butane lighter right here. You can tell I got this from Yellowstone. So I was out camping and I want to have a backup to my matches. Can you see, if I zoom in on this, or if I bring this up here, can you see the liquid in there? You see that? And here, when I click this, you can see that the flame starts. And if I put the flame out and still hold the bottom here, what's going to happen here is that this will empty out. Why does this empty out? And why do I not see any liquid coming out of the top? And the answer is very simple. This liquid turns into a gas when I hold this down. So when I open up the opening between the liquid in here and the outside air, the liquid becomes a gas. So how is it that this gas has been turned into a liquid? And the answer is under high pressure. So there's a lot of pressure inside of this lighter. And that's why if I were to take this and strike it with a hammer, this thing would actually kind of explode because there's high pressure. What's another way to turn a gas into a liquid? And that's under cold temp. Now, do you remember that the kinetic molecular theory of gases says that the collisions are elastic? Well, under cold temp, the loss in energy is significant compared to the energy that the molecule has, so they might end up sticking together. So when is an ideal gas not an ideal gas? When it's a liquid, which means it's either under high pressure or under cold temp. Another example of a gas under high pressure is the propane bottle. If you've ever gone camping, how do you tell if you still have propane in your tiny little green propane tank? Well, I'll tell you, what you do is you shake it. And when you shake it, you're listening for how much liquid is in there because it's not an ideal gas anymore. Okay, so when we talk about really cold temps, we're talking about close to 0 degrees Celsius, 0 Kelvin. High pressure, we're usually talking about 10 atmospheres of pressure. So other than that, gases are ideal. But there's also something called the van der Waals equation for non-ideal gases. Now, non-ideal is different than not an ideal gas. Non-ideal gases are all gases. Okay, so these are real gases under 1 atmosphere, 20 degrees Celsius, in that range. We've got an equation that looks like this: P plus A n over V squared is V minus Bn nRT. So this is the equivalent of the pressure, and this is the equivalent of the volume. And what you should know about this is that this is a correction based on the idea that when we have a gas, we use this as the volume. But in fact, if you were to take these molecules and condense them into a liquid, the real volume is less than this volume because the gas particles take up volume. So this is a correction factor for the fact that the volume that we use is different than the real volume. Now, how different is this? Well, if you had 22.4 liters, this volume here would be along the lines of maybe 20 milliliters. So it's not significant. This is a correction for the inelastic collisions. So the pressure that we actually use when we use the ideal gas law is less than the real pressure that should be there because there is some loss for collisions. Now in these formulas, what is N? N is the moles of gas. So naturally, the more moles of gas, the bigger the correction here. And actually here, more moles of gas, the bigger the correction. V is volume. A is the character of the molecule. So B here is the character of the molecule. Larger the molecule, bigger the B. Here, the more sticky the molecule, the larger the A. So this is an equation that I'm not asking you to memorize, but I do want you to understand that this Bn is a correction for the size and moles of the molecules. And the A N over V squared is a correction for the stickiness of the molecules. And that's what I want you to really know about the van der Waals equation. Any questions there? Are we good? I don't know why, but time really flew by today. It doesn't feel like we've been on the horn for an hour and 25 minutes, but we have. So sorry about that. Turn on your mics and say good day.
See you guys.
And
Bye.
remember,
Thank you, everyone.
your next quiz on this chapter is Monday.
Yeah.
Later today, I'll be posting a lab for you to do that as a gas lab. I was going to have you do it, but I found out that the materials I gave you, the acid bottle is leaking a little bit, and that makes it a little dangerous, so I'm not going to have you do it. Instead, it'll be a demonstration. It'll be fairly easy for you to follow, I think. And then we'll have one more lab next week where we're going to make aspirin. And I can't have you make aspirin at home. I was going to try to have you do that, but it's not possible given the materials I gave you. So I'm going to demonstrate that for you this weekend, videotape it, and post it. And there'll be a lab about that. Now, for those two last labs, one of them I'm actually going to have you write up in your lab notebook. The other one, I'm not. Both will have assignments. Okay? So I've been trying to be a little easier on you here at the end, where I'm not having you write stuff in your lab notebook as much, because I know we are pressed for time. I know you have other classes, and I know the semester is coming to an end. But on the other hand, I do want you to write up one more lab notebook thing. Capiche?
All right.
Have you guys noticed about that? No lab notebook, and you've been thinking, oh, gee, when's he going to post it? I'm not going to. So you don't need to not say anything about that. I've been doing that on purpose. Capiche?
Yeah.
Okay. I want to know how many people thought, oh my God, he's going to put some lab notebook stuff all at the end. Anyone? None of you were worried about it, huh? It's okay. I would have been too. I would not have wanted to ask me about that, because I might, he might have said, oh, shoot, I forgot. Yeah, I better post those. But I didn't forget. I purposefully left them off. All righty. So 2 more labs. Your next quiz is Monday, and then the last quiz will be next Friday. During finals week, we're supposed to have 2 meetings, one for the final for the lab and one for the final for the exam. One of those days, Tuesday, will be the exam 4. Wednesday will be the final. All right. Have a good weekend. Study hard.
Yep.
Yeah.
And remember, you tell all your family members, I'm busy. I don't have time for you. And Harry, no more walks. You don't have time for it.
No, not this weekend.
Okay. We'll see you all later. Thanks
Right.
for coming. I really appreciate it.
Yeah.
All right. Bye-bye.
Bye.
Bye. Bye.